have homework due today. And fun just keeps rolling. All right, so let's review what we talked about last time. And what we're talking about is the theory of tensors in quantum mechanics, which is very important if you want to understand the interaction, say, of electromagnetic fields and matter because of the nature of the multipole moment decomposition of the interaction of fields and charges. That's one place to see it, but it's not just in electromagnetic fields, also in nuclear physics, and the interaction of strong color forces with quarks and gluons. So it's an important general subject. Okay? But of course our focus here will be in the realm of interaction of atoms and photons. All right, so to do that, what we did, we first reviewed the notion of what we mean by a tensor. So a tensor is a geometric object, and it is defined by what happens under a three-dimensional rotation. Okay, that's what defines what we mean by a tensor. Okay, so we can think about, we have some geometric object here, which generally, if it's a rank K tensor, then that is an object which has 3 to the k different components with respect to some Cartesian coordinate system. Okay? And with respect to these coordinates, these are its components. Okay? So it's rank K, and each of these indices goes from 1 to 3. But that's why there's 3 to the k different elements here. Under a rotation, the geometric object gets rotated to another geometric object, and that new geometric object has components with respect to this coordinate system, and though what defines it to be a rank K tensor is if the components with respect to the rotated object are related to the components before the rotation by a series of rotation matrices. That's what defines it to be a rank K tensor. Okay? So these R's here are the elements of a 3x3 matrix, which define a rotation matrix in 3D. And the rotation matrices, their defining property is that their inverse is their transpose. Moreover, we're talking about a proper rotation. A proper rotation preserves the handedness of a right-handed coordinate system. It can't switch x into y and y into x without doing an inversion. So if we're talking about proper rotations, those have determinant 1, and so the set of matrices that define this property are orthogonal matrices in 3x3, and they're special. So they're special orthogonal matrices. They're special because they have determinant 1. So that's the set SO3, which also, as we discussed last time, forms a group. Okay? So examples of tensors, a rank 1 tensor is a vector. So a vector is a geometric object whose components rotate with respect to one rotation matrix. Okay? An example of a rank 2 tensor is a dyadic. Now, not every rank 2 tensor is of this form. Okay? But this is an example of a rank 2 tensor. And this dyadic, we should think about this just like the outer product we have of Graz and Ketz. That dyadic transforms as a rank 2 tensor because each vector rotates, and so you'll have 2 rotation matrices, and that's a rank 2 tensor. Okay. All right. Now, as we discussed, and it's very important in our ability to understand the quantum mechanical properties of tensors, is the fact that these rotations form a group. And in particular, they form a Lie group. A Lie group is a group that's also a continuous set, and that continuous set lies on a smooth surface that's locally flat. And that loosely is what it means to be a manifold. Okay? And the point of that is that every element of the group can always be expressed as being generated by another set of objects which lie in what's called the Lie algebra of the Lie group. And the Lie algebra is a vector space of dimension, the dimension of the surface that defines the manifold. And it has one extra structure on it. It has this thing we call the Lie bracket, which we should just think about, in our case, we'll think about these as matrices. It's just a commutator. Okay? Right, so for example, as we discussed last lecture, the Lie algebra associated with the Lie group SO3 is the Lie algebra little SO3. That is, well, as we showed last time, that set is the set of all antisymmetric 3×3 matrices. Okay? That algebra is a 3-dimensional vector space, and it is spanned by, for example, a set of matrices that are, whose matrix elements are related to the completely antisymmetric tensor epsilon ijk. Or equivalently, as we often like to do in physics, we often like to factor out the I. You can factor out an I, and then this is a set, a particular set of Hermitian matrices. That's the same thing as it defines out Lie algebra. And the Lie algebra here is defined by the bracket like that. Or equivalently, in terms of the J's, it would look more like the familiar angular momentum. Okay, so let me just write that over here. Since I don't have any more room, it can also be expressed in terms of those matrices J. Okay, so that's another way of expressing the Lie algebra of the Lie group, SO3. All right, so that's what we had for SO3. Generally speaking, as we discussed last time, we can always look at, and it's a very important thing to do, what are called representations of the group. So a representation is an homomorphism mapping one-to-one that maintains all of the structure of the group, as we discussed last lecture. In particular, we can map elements of the group onto matrices. Now, this was already a set of matrices. So in some sense, in this case, the group SO3 is a group of matrices. That's what defines it. That's the defining, but you could call that the defining representation. We can map each 3 by 3 matrix in SO3 onto other matrices that are maybe 5 by 5 matrices. That would be a 5 by 5 matrix representation of SO3, as long as it preserves the group structure, meaning that the matrix product, it gives us an element that is a one-to-one mapping with the identity and inverses appropriately chosen, okay? Now, as we discussed, we can say that there is an equivalence class of representations. If the only thing that I get from one representation to the other is by just changing the basis in which I'm doing a similarity transformation. This is the basis that defines the elements of the matrix. Then this representation is equivalent to this representation. Okay? Okay? Now, it might be the case that for a particular choice of basis, the matrix representation we've chosen for every element in the group is block diagonal. Okay? It might be the case. We'll see a case like that soon. If that's the case, then this representation is said to be reducible. It is reducible because each of the blocks then are themselves a representation of the group. Because if I multiply these matrices of this structure together, well, it's not going to mix the blocks. The blocks will multiply into another. So this is one little, composition law. This is a different it all does the same composition law, but in different ways. This might be a 1 by 1 matrix. This might be a 2 by 2 matrix. This might be a 137 by 137 matrix. It doesn't matter. Each one would be independently a representation of the group. So the fact that I can, in some sense, decompose this, I can reduce it to smaller block. Each one is, it's called a reducible representation. If I can't do that, if there exists no similarity transformation, no change of matrix basis, such that I can get block diagonals, if it's already one block and can't further reduce it, then it's irreducible. And that's what we call an IRREP. For short, an irreducible representation of the elements of the group. Okay? All right, so that was our a lightning tour of rotations and group theory. So then we turned our attention to, well, what does this mean in the context of quantum mechanics? All right. So in quantum mechanics, since tensors are defined by their behavior under the action of a three-dimensional rotation, what we looked at is the rotation operator in quantum mechanics. Remember, all angular momenta are units of h bar, or equivalently, we're setting h bar to 1. Okay? So this is the rotation operator written in a particular way in terms of an axis and an angle. So a vector operator, it's got all kinds of doodads and decorations on it. It's a vector operator, meaning that it's a collection of 3 operators with respect to a Cartesian coordinate system. And Under a rotation, this vector operator goes to a different vector operator. So what it means to be under rotation is that I do a unitary transformation on these operators, each of these operators, according to the rotation operator. Okay? And what makes this a vector operator is that the three components of the rotated vector operator are related to the three components before the rotation by the same rotation matrix that we had in classical physics. This is always confusing, right? There's two kinds of spaces, vector spaces, we're dealing with. There's three-dimensional space. Here we are. There's Hilbert space. Okay? That's a different vector space. There's two mathematical structures. They're two great tastes. They go great together. All right? So this operator is acting on Hilbert space. Right? It takes kets to kets. This operator acts on three-dimensional space. Okay? Keep that in mind. All right, so generally we define a tensor operator, what could be better than that, as, again, it's a geometric object which has 3 to the k components. There's operator it has each one of these indices goes from 1 to 3. So it's a collection of operators with respect to a three-dimensional basis in three-dimensional space. Okay? This is not a representation in Hilbert space yet. This is, I haven't written this in Hilbert space. There's a set of operators. There's some operator T11 if it was a rank 2 tensor. There is another operator T32. Okay? So it's a collection of operators with respect to a three-dimensional basis. And again, it is geometric and it rotates. So there's a rotated tensor rotated by the rotation operator according to the unitary transformation. And what makes this a rank K tensor operator is that the components of this rotated tensor are related to the components of the unrotated tensor by the collection of rotation matrices. Okay? All right. Anybody have any questions so far? Yes, please.
So D acts on an operator value vector or an operator value tensor.
Yep.
It'll actually change the operators.
Correct.
But the R's don't change the operators, it just mix them together in different ways. But it won't change the operator, it'll just change the components. But it won't change the operators. I don't know how to say that.
Let me see how I can try to. So what's boxed here, let's talk about a vector. Okay, let's start with that. So let's just look in 2D space. Here's a vector V. Okay? This is a different vector from that. Okay? This is the vector V, this is the vector V prime. However, the components of this vector are related to the components of that vector, right? So the components of V prime are related to the components of V through a rotation matrix, okay? So it tells me how to mix the components together to get these components, right? Similarly speaking, I can say there is a rotated vector, which is rotated according to the unitary transformation. And that new set of operators are related to the unrotated set of operators by this rotation matrix. And similarly, for any rank tensor. So it's a rule that says, geometrically, I rotate the object, but that rotated object its components are related to the unrotated object through this rule. I don't know if that answers your question. Yes, sir.
Yeah, so I was going to ask, the operator structure of our T and our V is pretty much the same. The way that it transforms from the original operator to our rotated operator, DE deck, for both the vector and the tensor. And
yes.
the rank.
So this unitary transformation
has no dependence on rank.
It's no dependence on rank.
Form, yeah.
Right. No dependence on rank. This is basically, I mean, what it's saying, what you want to be true is that if I have some rotated ket, okay, so this is the state, and this is the rotated state, okay? I want it to be the case that if I rotate the world, I can't tell the difference.
Yeah.
So if I rotate the states and the operators, the matrix elements should be the same. Okay? So that's where this is coming from. Yeah?
And that rotation, was that an SO3 or was it the...
Good question. We haven't gotten there yet. So R's are elements of SO3. That's what we just said. That's what we described. But I haven't yet said what these rotation operators are, what their group is. We're going to do that now. Excellent question. Let me just remind myself. There it is. Pardon me. Right. I guess before I do that, I wanted to say something about this in terms of the Lie algebra as well. Okay, we'll come to it. So, another way of defining a vector operator is by the local transformation for near identity, right? So if I have a small, if I look at a rotation operator for a small angle delta phi approaching a differential, right? That's the identity minus I, right? For small delta phi. Then it's easy to show, well, what we want this to be is the rotated vector. And the rotated vector for a small delta phi is just adding on a small component perpendicular to the vector, right? That's just geometric. That's what it has to be. Okay. So if that's going to be true, and if I plug this in, then this is equivalent to saying that the commutator, which direction? The I component with the j component of this. Jk. That's another way of defining this to be a vector operator, kind of a loop, if it has that commutation. For example, we've seen that in the past, in last semester, if I looked at the orbital angular momentum, then we saw, for example, Li with the positions, right? That works. So x is a vector with respect to orbital angular momentum. Okay, so we say v is a vector with respect to rotations generated by J. So this is an example where x is a vector with respect to L. Here's another example. Suppose let's define J as L plus S. This is the spin. Angular momentum. Question. Is the position vector a vector with respect to J?
No.
J doesn't operate on the same space as x, as the x tensor something a spin.
Well, so x, I can think about now x as being extended to x tensor the identity on the spin space. Okay? So that's what I mean by that. And now I ask you, is x a vector with respect to J? How would I do it? Well, I'd plug this in. Well, this is just, I mean, the fact that the identity is there doesn't do anything. This is still I, epsilon, I, j, k, x, k, you know, tensor identity by pair. And what about this?
Zero.
It's zero. It's commutes. So, is x a vector with respect to j? Yes, it is. Okay. We'll come back to that. That'll be important. All right. So now let's start to answer the question that you raised me about SO3, etc. Okay. So let's consider rotations on spin 1/2. Okay. So my rotation operator is e to the minus I theta, and my n dot j, j is sigma over 2. Okay.
Oh, so the J changes depending on
It is, it does.
Okay, okay.
So that's for some, right now, I'm restricting this, we're gonna look more generally, but let's say that we're, for the moment, restricting our Hilbert space to be a two-dimensional Hilbert space associated with a spin 1/2 particle. We want to talk about the most general situation, in which case we would have all possible J's and L's, right? We'll come back to that. But for the moment, let's just consider this, okay? Of course, we know that this can be written right? This is sigma sub n. All right. Now, this, let me call this that, just to emphasize that we're looking at J with a half. Okay. So let's consider a sequence of rotations. So I'm going to look at the group composition law, where I rotate about the same axis twice. Okay? So of course, that's the same thing as rotating around the axis once by the angle 2 theta. Just combines, right? So this is a group composition law. So let's consider the case where theta is pi. So I'm going to rotate around the axis n by the angle pi, and then I'm going to do it again. Right? Now, what is this?
Just the identity.
You would think, but it ain't. Look at this. This is cosine pi times the identity minus I sine pi times sigma n. Sine of pi is 0, but cosine of pi is minus the identity. So, what we see here is that these matrices are not representations of SO3 because they don't respect, no RSPECT, of the group composition law. Under SO3, if I rotate about any axis by pi twice, no matter what rotation axis I choose, if I do that twice, I get the rotation around 2 pi, which is indeed the 3 by 3 identity. So that's the group composition law for SO3. But this does not respect that. So that what we learned, first of all, is that this, we're going to come back to this for the general J in a moment, are not reps of SO3. But they are a group. What group is it? Well, so what we see here is that this set with respect to any basis in 2D Hilbert space that this set, they're 2 by 2 unitary matrices. Okay? That is the set U2, excluding bottom. That set is not the whole story, though, because this is not an arbitrary set of unitary matrices, they're special. Why do we see that? Well, what is the determinant of one of these guys? The trace is 0, but the determinant is not. The determinant is the product of the eigenvalues. Close. Close. Not get a cigar.
But in the exponential, right?
So what are the eigenvalues of this matrix?
E to the plus or minus I big over.
Right. One of them has an eigenvalue to the plus or minus. So it's this times that. Those are the two eigenvalues of that matrix, right? Because the eigenvalues of the sigmas are plus or minus 1, so the eigenvalues of the unitaries are this, and that product is 1. So it's a special. So it is the group SU2. Okay? What is the Lie algebra of SU2? It's a Lie group. What is the Lie algebra? Yeah, sort of. Close. Well, good guesses here. So, what do we mean by the Lie algebra? Well, remember what we said is that in this case, if G is in the group SU2, then G can be written as the exponential, and we always, in quantum mechanics, factor out the I times the sum of some AI, I equals 1 to the dimension of the, I'll call it, and some EI, right? Or I can call them capital AI. So AI are the basis elements of the Lie algebra. Okay? So for example, back there on that board, go pay attention, back there on that board, right? We said for SO3, we could write an arbitrary element of the algebra as a linear combination of these three basis elements of the Lie algebra. So what is an example of a basis for the Lie algebra here? The Pauli matrices, right? Or the Pauli matrices over 2. So the Lie algebra here is spanned by sigma 1 over 2, sigma 2 over 2, which is sigma x, sigma y, and sigma 3. Right? This is J1, J2, J3. Okay? So, this Lie algebra, what is it? It's the set of traceless 2x2 permission matrices. It's not the set of all permission matrices. There's one that's missing. The identity. That's because it's special. Because if I included the identity, I would have had something whose determinant wasn't 1, right? So we can always write any element of U2 as either the I, because some phase phi naught, times an element of SU2, where this is the identity. Right? Yeah.
But isn't the determinant of the identity 1?
It is.
But it's not.
Oh, no, no.
traceless?
It's not. Yeah. Good point. Let me think about that. No. It's okay. Yeah. Here's the deal. Yes. The identity has determinant 1, but we're not asking about, so let me try to be clear here. There is the group SU2. SU2 are the group of unitary matrices with determinant 1. Here is an example of a unitary matrix with identity, whose trace is not 1. This is a unitary matrix, but its determinant does not equal 1. This matrix is not in SU2. This matrix is either the I times the identity, which means the identity is not in the algebra. Because if I exponentiated it, I would get this, and that ain't in SU2. Because its determinant is not 1. Okay? So, the Lie algebra here is the set of traceless permission matrices. Those are the ones which, when exponentiated, give us determinant 1 elements of the group. Okay? And the Lie algebra here satisfies the Lie commutators, which is the standard algebra that we know of angular momentum. I satisfy that. Okay, so that's the Lie algebra. Now, I claim that the operators, the set of operators, now, let me write it this way. Okay, so these are the matrix elements. So let's fix J as arbitrary. J could be a half, it could be 1, it could be 3 halves, it could be 2, it could be 5 halves, it could be 3, etc., etc. Okay, so I'm going to fix J as one of these things. This are elements of a 2j plus 1 by 2j plus 1 matrix. Right? So if j is a half, these are the elements of a 2 by 2 matrix. If j is 1, this is the elements of a 3 by 3 matrix. J is 3 halves, the elements of a 4 by 4 matrix, etc., etc. I claim that these matrices are representations of SU2. They are all reps of SU2. What does it mean to be a representation of SU2? It means it respects the group structure. It means for every element in SU2, if G1 is in SU2, and G2 is in SU2, and G1 composed with G2 is equal to G3, which must be in SU2, and this is the identity operator in SU2, and there exists a inverse element in SU2, that the map that takes G to one of these matrices respects all the above. In other words, I take every element, every 2 by 2 matrix there, and I map it to a 3 by 3 matrix. And then I look to see whether the product of those 2 by 2 matrices gives me another 2 by 2 matrix. And if it respects all of that, it respects the group structure. Now, note, it's not, as we discussed, the mapping need not be one-to-one. I can map, for example, we talked about the trivial representation. I can map every element in the group to the identity. That's a representation. It's a pretty trivial and stupid representation, but it is a representation. But the fact that for the integer a momenta we don't have that -1 doesn't bother us. It still is a representation of SU2. Yes?
What's the map for this specific case?
What we have to do is prove this. Right? We have to show that when I take elements of this operator and map them, then they respect that. But that will be obvious when you do it.
Is the mapping just taking the JM prime and JM on the other side?
Well, so what we have to show is, if we looked at for the SU2 case, right, we had these guys. Now we have these more general things. But because, as long as what's important here, what's crucial here, is that this is the same Lie algebra. It's through those commutators that it all works. In other words, it must be the case that for any j, I always have this. And then when I compose them, they will do the same thing that the sigma matrices do. Yes?
So you can have a representation of SU2 that's a bigger matrix than a 2 by 2?
Yet,
And you have an irreducible one that's bigger than a 2 by 2?
indeed you can. So all of these, moreover, these are irreducible representations, all of them. So we have the irrep of, that we just described, of 2 by 2 matrices. In some sense, that's the defining representation. But now I can look, for example, at a spin 1 particle, or equivalently, an L equals 1 orbital angular momentum, and calculate these matrices. Well, there's no further way to block diagonalize them. They are already as diagonalized as they could have been. There's no way to go further. So they're all, for every J, each one, this is a 2 by 2, this is a 2-dimensional irrep. This is a 3D irrep. This is a 4D irrep. This is a 5D irrep, etc., etc. These are all the irreducible representations of the group SU2. Now, back to your question, Steve. What about SO3? Is this the same thing as SO3? Well, no. But it's darn close. You can think about, I mean, there's a complicated relation in terms of the structure of the manifolds and surfaces, but SU2 and SO3 are kind of related. They're not isomorphic, because we just showed there are the group, the defining composition laws of SU2 are defined by the Pauli algebra that we described there. And we have this thing where you rotate by pi, and then you rotate again. You don't get back the identity matrix, you get this -1. But it's there is a 2-to-1 mapping from SU2 onto SO3. Okay? That is to say, so the group SU2 is what we say is a double covering of SO3. This isn't so important for our discussions. It's a technical point. They're intimately related, but that double covering, you see, if I come back to this board over here, let's look at this. Suppose we did a rotation by 2 pi on a spin 1/2 particle. Okay. Well, this would be the minus the identity, and this would be minus the identity. It wouldn't change this. That minus sign doesn't affect how the components of the vector change. It does affect the quantum mechanics of the probability amplitudes, as we saw, but it doesn't affect this. All right, so we learned one important thing, that the group of geometric rotations in quantum mechanics, the things that rotate in 3-dimensional space, that group is the group SU2. Moreover, when restricted to a definite amount of total angular momentum J, the matrices that are 2J plus 1 by 2J plus 1 are all irreps of SU2. Now let me ask you the following question. Let's consider a d-dimensional Hilbert space. Okay. E.g. D D is a spin J with dimension 2J plus 1. Okay. I can consider the set UD. This is the set of all D by D unitary matrices. Okay, I can consider that. And that set is a Lie algebra that is generated like this, where H is the set of all Hermitian matrices. Right? So if I take an arbitrary D by D Hermitian matrix and I exponentiate it with an I, it's some unitary matrix, right? So the set of all Hermitian matrices is the Lie algebra for the group UD. Now I could also consider the set that also has determinant 1, which means I get rid of the identity, which is sort of the trivial one. So I can consider this is the set of unitary with determinant 1, and this is a set of all traceless Hermitian matrices. This is the group SUD. Now I ask you, is the group SUD equivalent to a representation of SU2 for anything bigger than spin 1/2? No, it is not. In other words, there are things we can do in Hilbert space which are not equivalent to a geometric rotation. In other words, for example, suppose I have a J equals 1 spin. And suppose I have the state psi, which is the state with maximum projection of angular momentum. Okay, so let's suppose I have that. And suppose there exists a unitary transformation which, for example, can take that state to any other state. And suppose I take it to the state m equals 0. There exists a unitary transformation on Hilbert space which can take me from this projection to that projection, because any state can be mapped into any other state by a unitary. But there's no geometric rotation that can do that. Every geometric would take maximum projection to maximum projection along a different axis. So in other words, if U is in the group SU2, then that is something that would take, if this was the z-axis, then this U would take this just to maximum projection along the rotated axis. If it's maximum projection along that axis and I rotate it, it's maximum projection along that axis. There's no way to get from m equals 1 to m equals 0 by a geometric rotation. This would be some other kind of unitary that's not equivalent to just a geometric rotation.
When you say geometric rotation in 3D?
Exactly. That's a good point. There's, of course, different kinds of geometry. What I'm talking about here is the rotations in the geometry of three-dimensional space. So what this is to say is that SU2 is the set of these guys But this is not the set of all unitary matrices, except for one case. Spin 1/2. For spin 1/2, all you could do is rotate the direction of the spin. Spin up along this direction becomes spin up along some other direction. So it's kind of weird. And spin 1/2 is kind of the most classical in a certain bizarre sense. It's only just geometric. That's why we can talk about the block sphere for spin 1/2 and map every single state in Hilbert space as just a direction in space. But for higher spins, we can't do that. Let me ask you a question. What is the dimension of the Lie algebra associated with the Lie group SUD for an arbitrary D?
2D plus 1?
It's a good guess, but it's a guess. It's not quite right. In fact, it's not right. How would we know? What does it mean to be the dimension?
How many parameters you need to describe the matrix?
Indeed.
So we don't need quite d squared because there's a constraint of determinant equals 1?
Yep.
Okay,
D squared minus 1.
okay.
Yes. Good job. So, the dimension of the space is dimension of the space, SUD, or the algebra, is D squared minus 1. So I can parameterize an arbitrary U, if U is in SUD, then I can write U as e to the minus I, the sum over some parameters where the set E sub I are traceless Hermitian D by D matrices. For SU2, those are the Pauli matrices. For SU3, well, we don't know. But there are matrices. There's something called the Gelman matrices. They are the generalization of the Pauli matrices as a basis of traceless Hermitian matrices. All right, very good. Let's continue then, and I'll come back over here and talk about now what if I have two spin 1/2 particles? So let's consider the case consider rotations on the space of two spin 1/2 particles. Okay. All right, so my Hilbert space here is the tensor product of the Hilbert spaces, each 2D Hilbert space, right? I claim that if I look at the tensor product of two rotations, so each one of these guys is my usual rotation operator. represented in the standard basis. Okay? That this is a representation of SU2. Okay? In other words, an element of SU2 is defined by an angle and an axis, right? I claim that if I apply the same rotation matrix this way, that this is, that the set of all of these guys is a representation of SU2. Why?
Because they both just act on the one particle separately?
Yeah, RESPCT. It respects the composition law, right? Because each one, if I look at the composition of two of these, well, each one of these is going to do the same thing on each, right? And then it's just going to be the appropriate rotation. That's the composition of rotations on each atom. So let's look at that. So this is represented in the standard basis. What's the standard basis? The standard basis is the product basis. Up, 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 down, down, up, down, down, right? That's the standard basis. This is the basis. Up, down, tensor with itself. So that's the standard basis. So let's do it. Let's consider, for example, let's look at one of these elements for some particular case. So let's consider rotation around the y-axis by pi. Let's just look at one of those elements, okay? So for this guy, pi equal to half, theta equals pi. The axis is the y-axis. That's cosine pi over 2 times the identity minus I sine pi over 2 times sigma y. Okay?
You didn't write the I.
Yeah, I left that. Yeah. Okay? That's important. That's equal to minus I sigma y, right? Which in the standard basis of up and down is minus I times the Pauli matrix, which is minus 1, 1, like that. Okay? So now, on the space, this matrix the matrix representation, as written, is this 4x4 matrix. Okay, so this is the element of SU2 corresponding to this. Now, I ask you, is this representation irreducible? Kind of, but not really. Remember, it's got to be block diagonal. This is block off diagonal.
Can we just rotate the whole thing back?
Well, yeah, we can kind of rotate. So this is not an irreducible representation. I claim I can reduce this. I claim I can find a basis in which this matrix is block diagonal. This isn't. This is block off diagonal. Wrong answer. Thanks for playing. We have, so I claim that this is reducible. In fact, I claim to reduce it. I can find a basis in which this is block diagonal. That's what it means to reduce it. Block diagonalize this matrix. This matrix can be block diagonalized. Which is to say reduced. What basis? Well, in this case it's obvious because of the following. Because this thing does the same thing to both spins, if I'm in a subspace which is symmetric, it keeps the subspace symmetric because it does the same thing to both spins. If the subspace is antisymmetric, well, it stays antisymmetric. So I claim block diagonalization in the basis up, down, minus down, up, 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 down, plus down, up, down, down. So this is another basis. It's a familiar basis, right? This is the spin singlet. This is the spin triplet. Right? The spin singlet is antisymmetric with respect to exchange of the spins. The spin singlet is symmetric. This matrix doesn't mix symmetric and antisymmetric spaces. So there's no off-diagonal elements between these guys. Okay? And we'll finish this next time, but I just want to say one thing here. I'll just write it down and we'll come back to it. In this basis, this guy, in this basis, so-called irreducible basis, looks like this. This is block diagonal. This is the 1-by-1 block corresponding to the singlet. This is a 3-by-3 block corresponding to the triplet. Moreover, what defines these blocks is this has a total angular momentum spin 0, and this has a total spin angular momentum of 1. This is the coupled basis. And this is truly important. This is going to be an important story. That with respect to the coupled basis, we have irreps. With respect to the uncoupled basis, it's reducible. So we can think about what the rotation does is it does something to the singlet and something to the triplet. We can decompose the state into some amount of singlet, some amount of triplet. It does nothing to the singlet and it rotates the triplet in these two blocks. And we will pick that up next time. All right, heavy duty.